see, not everyone's here. Oh well. There's, pardon me?
Steve's got a long commute.
Yeah, a long commute. He lives on campus. You guys know that? He's one of the selected few. I don't know how that works. I don't understand it. There's an experiment this week, right? Helmholtz resonator. There'll be a lecture on Helmholtz resonators Thursday before the experiment, okay? Last lecture we talked about radiation from a pulsating sphere. It's a spherically symmetric situation, isotropic radiation. And it's important because we showed that when you have a small source, and that means the source is small compared to the wavelength, it radiates isotropically. There's so much diffraction there at this long wavelengths that it's the equivalent to a pulsating sphere. So that's why it's good to have all the theoretical results for a pulsating sphere. We can carry them over to any small source. We just have to use the same volume, velocity, amplitude. The moving surface area times the peak velocity, and we're going to see more of that today. We also looked at acoustic reciprocity for small sources. And the simplest way of thinking of reciprocity is you could have a very complicated situation with a source and a receiver. And the receiver's picking up some pressure amplitude. If you swap the two, you pick up the same pressure amplitude. Assuming the volume velocity amplitude stays the same for the source, okay? That it doesn't change because it's in a different environment. That's a fine point. We looked at some examples of that. We want to look at a third example right now. It's a naval example. And I picked up on this from some old notes by Sanders. He's the S in KFCS. He's retired now. The rest of them are dead. And it's a lengthy calculation that he did. Really lengthy. If anybody's really interested in this, let me know. I can probably dig it up somewhere. I'm pretty sure I don't have a digital copy, but I can scan it. So here's the idea. You have some underwater source, a vehicle, and typically in this case, it emits broadband noise, a continuous spectrum, plus some spikes, which are called tonals. These are pure tones. And the situation that we're imagining here is we have this source here that's moving around. Okay, it's an underwater vehicle, and we have a fixed hydrophone. Okay, this could be attached to a mine, I guess. The source is moving around. Well, if you consider let's say one of the tonals, one of the pure tones from the source, it's going to cause, there's going to be an interference pattern here where you have pressure nulls. And the reason is, you remember, when you have a source like this, that the way we meet the boundary condition here of no pressure is we imagine an image source over here. And when you have a two-point source, you get a nice interference pattern, as we've discussed and demonstrated in the anechoic chamber. The problem here is that this source is moving around, this interference pattern. Again, these lines represent the nulls. They're going to be moving around. I think it's very hard to deal with that calculationally. It's much better to imagine, instead of the hydrophone being fixed and the source moving, imagine the source to be fixed and the hydrophone moving. And reciprocity shows that those two are essentially the same. Surprisingly, not obvious. Reciprocity is not obvious. There are simple symmetrical situations. If you look at the list of examples yesterday I mentioned, there are simple situations where you know reciprocity holds due to symmetry. But it holds in general, in asymmetric situations like this. So anyway, what you can do here, and this is what Sanders wrote up in this lengthy document, is you can actually track this by doing a calculation here. And receiving, from the information received by the hydrophone, you can actually track that source. And in particular, I remember he found the distance of closest approach. Okay? So that could be useful if you want the mine to detonate, okay? You want to make sure it's a foe and not a friend, though, I suppose, okay? That's your problem. All right. So anyway, that's another example. You can see that this is similar to the audiophile thing, to the properly arranging loudspeakers in a car so you optimize the sound. Remember we talked about yesterday? It's a similar idea. So we're going to, for future use, including today, we're going to summarize and slightly recast our information, results that we know for a small source, which KFCS call a simple source. And occasionally I'll call it a simple source too, because it is simple. Okay, and here it is. All that's important here is the velocity amplitude. So this holds not just for a pulsating sphere, but any small source, right? And the important drive parameter is the volume velocity. It's simply the moving surface area times the peak velocity of the surface. That's the so-called source strength. Here's the instantaneous pressure. It falls off inversely in distance. It's got the usual propagating factor here. It's a spherical wave. It's a spherical wave, an isotropic spherical wave. Here's the amplitude. Now you'll notice there's been some recasting here. We're putting the pressure in terms of the volume velocity, and you'll see why that's important. We're going to use that in our next calculation. The intensity, which is given by this, if we put it in terms of the source strength, it's equal to this. And here's the power. The power here, for an isotropic wave, the power is very simple. It's just the intensity, the power per unit area times the area, which is 4 pi r squared. We call these KFCS calls these the free space relationships. There are no boundaries here. That's what it means. There are no boundaries. Another useful situation is when our small source here is near a boundary. Okay, and we're going to take a rigid boundary here, a large rigid boundary. And what do we mean by near? We mean near compared to a wavelength. So this distance right here, not only is the source small compared to a wavelength, but the distance to the plane here is small compared to a wave source. In that case, we know how to solve this. We imagine removing the plane and just putting an image source here that's identical to this in phase. That gives us the right boundary condition. And because this distance is small compared to the wavelength, it's as if these things are right on top of each other. You just get a doubling of the source strength. So here's the pressure. It's doubled from what we had before. Here's the pressure amplitude, which is just this part right here. It's, of course, doubled. Because the pressure is doubled, the intensity will be quadrupled, okay? Because it's proportional to the square, right? The power is only doubled, though. It's not quadrupled. And the reason is, here, we are not radiating, we're only radiating into a hemisphere here. So once you put this baffle here. So the intensity times the area is not 4 pi r squared, it's 2 pi r squared. So that brings the quadrupling down to being doubled. Okay. So any questions so far? Next, what we're going to do is, we talked about the 2-point source. That's the simplest spatially extended source. We talked about well, I guess that's not true. I guess the pulsating sphere is the simplest spatially extended source. Next, in order of complexity here, is what we call a uniform line source. And what it is we have a, let's look at the diagram. This is from KFCS here. Here's the line source. We'll call this the x-axis. So here it is. It's a pulsating rod, okay? And it's pulsing radially this way, all in phase. So it has some fixed length here, which we'll call L. And the radius here is sinusoidally oscillating about some equilibrium value. So you know that the radiation pattern is going to be symmetric. This is going to be an axis of symmetry. Whatever the pressure amplitude is here, it's going to have to be the same on a circle that's concentric here, because we have this axis of symmetry. We'll measure theta. Here's the perpendicular bisecting plane, goes through here, this perpendicular line right here, halfway. We'll measure theta from there, okay? And the problem here is to find the radiation field. And we're going to look in the far field instantly. You'll see that. Before we get to that, though, let me look at the notes here. Right. So this is the equilibrium radius of this rod here, this little bit right there. We're going to assume that it's much smaller than a wavelength. Okay? We're not going to assume that the length is much less than the wavelength. If the length is much less than the wavelength, we're done. How does this thing radiate? If the wavelength is large compared to the source, it's going to radiate isotropically. Right? We have extreme diffraction here due to the long wavelength, and we know how to calculate that. You just looked at the formulas. So we're going to, the length here is not going to necessarily be small. That's just going to be a special case of our calculation. Now, even though the length is not small, what about a little element of the source here? Oh, I think I missed something here. Hold on a second. Yeah, naval stuff here. So you've probably heard of a towed array. Maybe some of you have dealt with them. Right. This is similar to a towed array. Now, a towed array, I think, probably has discrete sources. Is that right? But if their spacing is much less than a wavelength, you can use the continuum theory here. So you'll do both of these. I think you'll do the discrete theory in 3452. You'll probably do it. I've got a feeling you're going to do that in the underwater acoustics course. We're going to do here just the continuous theory. Okay. So here we are. We can imagine this to be a collection of these little tiny sources here, right? Each of these little tiny sources of length dx, okay, is going to be a small source, right? Dx is, it's a differential, it's small. And of course, A is small, as by assumption, the radius here. So this is going to radiate as a small source. We know the pressure field due to a small source. Now we just have to integrate over all the individual sources there to get the total pressure. So we're going to use the volume velocity. This little elemental source here has a volume velocity. It's the velocity amplitude, which we're calling, again, capital U naught, times the, I'm going to add moving in here. Remember, it's the moving area. The end caps aren't moving. We don't include that in it's the area that's moving, of course, that's generating the sound. So what's the area of this cylinder here? Well, it's just the circumference times the length of the cylinder. So that's our source strength, elemental source strength, or volume velocity amplitude, dq. So the instantaneous pressure at some point here will be due to the sum of all the individual instantaneous pressures. Here it is for this little source right here. We've got to use this distance, which we're calling r prime, which is a variable, and we need to integrate over all this. I've substituted the wave number here to get rid of the wavelengths. Okay? And the reason we do that is, look at this thing right here. Ka, that's the dimensionless number that's going to be important here. Actually, Kl is going to emerge as important. But we always want to go to these nice dimensionless quantities here. K, the wave number times the length. Okay, now we need to integrate this over all x values, from minus L over 2 to L over 2. We need to integrate that. Before we do that, though, we're going to make an approximation here, a standard approximation. We've talked about it before. We're going to assume we're in the far field. The far field means that this distance r right here is much greater than the size than the length L. This is almost always the case, okay, and it greatly simplifies. We did that for the two-point source, remember? R is much greater than L. Now, let's go, this is very similar to what we talked about in the two-point source, but it's worth seeing it again. When R is very, very large here. This point is way up there. These two lines become very nearly parallel to each other. And what's important here is this the path difference is then this right here. All right, we can easily calculate that. This distance is x. This angle here is the same as that angle there. So the path difference is just x times the sine of theta. It's very similar to what same as we saw before, or very similar. So we can, so what happens is this. We can relate r prime to r. R is just what we call a field variable. It's fixed here. But r prime changes in the integration, and that's we have to take that. We have to deal with that. All right. But we can relate, and you can see it from here. You want to imagine these two things being these two rays or paths here being parallel. You can see that r prime is going to be r minus x times sine theta. Okay, where x is our integration variable, but r is fixed. Now, there's two things to notice here, and it's just like the two-point source. This r prime here is a variable. It varies about r, the fixed value r. And it changes just a little bit. Because this is so big, it's changing a little bit. We can just set r prime equal to r here. That's a good approximation. However, we can't do it here. We can't set r prime equal to r here. Because this is 2 pi over the wavelength. Right? And we don't want to make any assumptions. You know, this is not necessarily, this can vary a lot. As r prime varies, this can vary a lot, just like in the case of the two-point source. So there we have to include the path length. So again, this is just like the two-point source. A good approximation is to go ahead and set r prime equal to r in the denominator. But in the exponential, we have to put in our approximate, the fact that r varies. It is in general going to be important there. So when we make this substitution, and write down the integral, okay, and take everything out that doesn't depend upon x. You remember, r doesn't depend upon x, and certainly t doesn't. All these are constants with respect to x. This is the integral that we have to do. And let me remind you, theta is constant here, right? It's a field. It's telling us it's a field variable. The two. This is called a field point, okay, because we're looking at the pressure field. And the field point is specified by r and theta. And they're constant in the integration. So I don't have to worry about this. And if you look at this integral, at first it looks hard, but then you realize, well, theta is a constant, and k is, of course. We can do this, and this is easy, an exponential. Right? So it's just, the antiderivative is just itself, and you've got to pay attention to the chain rule here. So the derivative of this gives us the integrand, so we just evaluate it, and we get this expression right here. Okay, and then what we're almost always interested in here is the pressure amplitude. So we kill this, we don't worry about the I, and that gives us the pressure amplitude, capital P, and here it is. So that's the far field pressure amplitude for this pulsating line source. We're far compared to the length of the source. We're far away. But the wavelength and the side of the source can be anything. The wavelengths can be long or short or approximately equal to it. It doesn't matter. There's no relationship. We've left that open. This is a fairly complicated expression. And to understand it, we're going to do a standard thing here. And it works, as far as I know, it works for every other source. We're going to do this again several times. Different sources that we consider. So the way people beat this down in order to appreciate it is they separate the radial dependence and the angular dependence. Okay, they factor it. Now there's of course an infinite number of ways you can do that here. But here's the idea. You head towards this factored expression. There's this h of theta. This is called the directional factor. This is called the axial pressure. All right? So you may wonder, well, and I'll tell you right now, this is the axial pressure right here, and this is the directional factor. Now, how do I know to do that, right? You know, for example, I have this 2 here. Why can't I put the 2 in there? Well, there's something wrong about that. Let me explain to you what it is. The convention here is that and it's very convenient. The convention is the directional factor for theta is equal to 0 is equal to 1. Okay? Theta is equal to 0, incidentally, and we're going to go over this again. What happens if theta is equal to 0 in the far field? We're going to get a maximum, right? Everything's in phase here. The fact that this one is a little bit farther away than this one doesn't matter in the far field. That's negligible. So everything is in phase in the far. We get perfect constructive interference. This is going to be a maximum in the far field up here. And it'll be that way everywhere in the bisecting plane here because of the symmetry. As long as you're far away, it's going to be a maximum. So theta is equal to 0 is where we have perfect constructive interference in the far field. And for theta is equal to 0, it's by convention we set h equals 1. That will nail this factorization down so that it's unique. Okay. So let me just let me look at this in a few steps here. So we'll confirm that. But when you enforce this convention, you find, and we're going to find that just in a moment, that this is the axial pressure, and this is the directional factor. When theta is equal to 0, this is equal to 1. Can everybody see that? Well, it'll be recast in a different form on the next page. But as theta becomes small, the sine of theta becomes small, of course. This whole quantity will become small. So the sine of a small quantity is equal to that quantity in radians. So these two things, and when theta becomes very small, these two things, you can forget this sign. They cancel. You get 1. You get 1. So this axial pressure is the pressure on that in the perpendicular bisecting plane in the far field, where you get perfect constructive interference. And here it is, okay? And it's simple. It's falling off as 1 over r. And here's how we'll write the directional factor. We'll write it as a function, for convenience, a function of a function. So we're going to introduce this quantity v here, which is just this kl over 2 times the sine of theta. So our directional factor is the sine of v over v, where v is given by that. So we'll look at this soon, but first I want to make a few more, some comments about the so-called axial pressure. And again, here it is. If we can recast this in terms of the source strength. Remember the total source strength now, not the element. We've already integrated. The elements are gone. We've done the integral. But this source is going to have a total source strength. And it's going to be the moving area, which is the circumference times the length, times u naught. That's the source strength. When you put it in Q, when you put it in terms of Q, here's what you get. And I don't know if you recognize this, but it might look familiar to you. This is exactly what we found for a small source. It's exactly the same. So how can that be? We don't have a small source here. So how can we get the same answer? We have to explain that. It's actually simple. Remember, we're in the far field, and the axial pressure is on the perpendicular bisecting. It's on this plane, anywhere in this plane, far away, right? What do I see far away when I'm in this plane? Everything's in phase here. So even though the wavelength, even though the source is not small, everything's constructively interfering here. And that's what happens in a small source. In a small source, because the wavelength's so big, everything's in phase. So we have to get this. We have to get this answer. We have to get this answer on the so-called acoustic axis. We'll define that later. But on the axis here, It's perpendicular in the perpendicular bisecting plane. We have to get that answer, right? Even though it's not a small source. So that makes sense why we got that. It really has to be. So that's explained here, a lot of words. So now let's look at the directional factor. Okay, what is this? You know, everyone knows what the sinusoid is, what the sine looks like. This we can think of as, for increasing V, we can think of this as a damped sinusoid, okay? But it doesn't start out. Make sure you recognize something. You know, the sine of V, when V is equal to 0, is 0. But this, it's 1. The value is, as we discussed, it's 1 is equal to 0. So what it's going to look like, you know what it's going to look like. Here's a plot from KFCS. It's going to look like a damped sinusoid, where the amplitude is falling off as you get farther and farther out. And it's equal to 1 at 0. So this is the directional factor H as a function of V, which is this function right here. And typically, what we do in acoustics to understand and characterize a field, we look for pressure nulls, okay? So where's the pressure going to be a 0? Remember, the total pressure is the product of the axial pressure and the directional factor. So this can't be 0. But this can be 0. You can see it here. We can have nulls at these values of V here. And you know what they're going to be. It's going to be when V is equal to pi. Now, not 0. The sine of 0 is equal to 0, but the sine of V over V, and the limit as V goes to 0, is not 0, it's 1. But these are going to occur for V being pi, 2 pi, 3 pi, etc. And by symmetry, we can be on the other side too. We can have minus pi. V can be minus, the sine of minus pi is also 0. So that's what we look for to get an appreciation for acoustic field. Often we look at the pressure nulls, or sometimes the pressure minima if it's a more complicated situation. But here we have exact zeros in the far field. So you may wonder what happens as you come to the near field. Well, you're still I don't really know the answer to that question. It's hard to. I really did not want to get into this, but I opened my big mouth. Okay, so far away here we have a pressure 0. Okay, when V is equal to plus or minus n pi, we've got a 0. What happens is you come closer and closer to the source, and you stay on a surface of 0 pressure. Do you think that surface can just evaporate? I don't know. What I suspect is going to happen is here, that surface, here it's a cone, as I'll describe to you. The surface will start to distort, okay? And that's what happens for a 2-point source. If you have a 2-point source here, and let's say you have a pressure, the pressure is equal to 0. Okay, so there's, let's say, a half wavelength difference here. As you come in, this is a point on a cone here. Because if you move around here, the pressure is going to be 0. If you move around in a circle, it's concentric with this axis here. By symmetry, the pressure will vanish. So all of these points here lie on a cone. As you start to come in here, what happens to that cone? Well, it distorts and goes like that back to a cone. Okay, so this is the near field. Usually we don't have to deal with this. Usually we're only interested in the far field. So that's what happens to the 2-point source. I suspect that the rod will behave the same. It's hard to imagine that when you're coming in here that all of a sudden the pressure starts to not be 0 anymore, that you can't find a pressure null. That seems strange. But I have to be honest with you, I've never seen the solution for this. Incidentally, in the near, solving for the field, the near field here is not an easy problem. My guess is it can be done, but it's going to be difficult. Yeah?
Because you're getting closer than when you're in the far field, you can say that they're the same distance away, right? As you get closer, then that distance will change the intensity. Go ahead.
Well, yeah. It goes back to those two approximations. When you're far away, you can neglect the fact that this one's farther away in the denominator, but in the numerator, you have to take that path difference into account. If it's 1/2 of a wavelength, you're going to get a 0, right? So we made those two approximations. They fall apart as you come in closer, and it becomes a much harder problem. But you can bet it's probably somewhere in the literature, okay? And, you know, using Google Scholar, which is what everyone uses nowadays, you know, it's free, and it seems to be pretty accurate. You could probably find it, okay? Whether or not you can get the article, that's another matter, right? So the world is still struggling with getting journal articles free, you know, and quick and high quality. You know, that's what we're demanding, right? The publishers don't like that. They need to make money, so there's a little bit of a problem there. Okay, so this is the math. What are these things? What do these nodal surfaces look like? Well, it's very important for you to recognize it depends upon the KL number here. If KL is small, we have a small source. Where are the nodes going to be? No nodes. The source, this thing will radiate isotropically. There are no nodes. The wavelength is too big to find a 1/2 a wavelength path difference between some sources in there to get some destructive interference. It's not going to happen. So that persists up to a value of KL being 2 pi. When KL is equal to 2 pi here, substitute 2 pi in here. Okay, cancel the 2's. Cancel the pi's. I'm making this sound complicated. You can't find a solution. If KL is less than 2 pi, you won't be able, you can set n is equal to 1 here, the smallest value. You will not be able to find a theta value for which it's equal to 0. The wavelength's just too big, okay? Sine of theta is bounded by 1. The most it can be is 1. So if KL is less than 2 pi, you can see from here that you can't satisfy this. But once you're beyond once KL is beyond 2 pi, you're going to have one node. You're going to have one node. So what it'll look like is this. There'll be some angle here, okay, that if you go far away, the pressure will be 0. And it'll be 0 on this whole circle right here. And as you move out, if you stay at that same angle, it'll be 0. So we have a cone. There is a nodal cone in the far field. Again, it'll get distorted in the near field. So as we increase the KL factor here, we're increasing the frequency, we're decreasing the wavelength. We get more and more opportunities for destructive interference. So you can show, it's not difficult to show, and we'll do a homework problem on this, and there'll be a quiz problem, that when KL is between these two values, you just get one nodal cone. Now, technically speaking, you also, by symmetry, if I've got a nodal cone there, I'm going to have one over there, right? By symmetry. That's why we have the plus or minus here. So it's really a double cone. You know, if you want to think of this cone, it's what we call a double cone. As you lower the wavelength or increase the KL number more, eventually get into a region where now you have 2 nodal cones. There'll be 2. So as you increase the KL number, when KL is low, when it's much less than 1, you have isotropic radiation, no nodes. As you start to increase the frequency, increase the KL number, or decrease the wavelength, eventually a node will appear. It'll come right out of the theta is equal to 90, plus or minus 90. It'll come out like that as you're increasing KL. And then it moves up there, and then another one will come out. And as you go to smaller and smaller wavelength, you get more and more nodal cones. With small wavelength, you got a lot of opportunity there to find a destructive interference. Now, I want to make sure everyone understands there's an elementary argument. We went through this calculation here and derived this rigorously. But there's an elementary argument to easily see why we have these nodal cones in a far field. Here's our source, our line source. Consider 2 elements here. One, for right now, one right at the end and one in the middle. Okay, little tiny elements. Forget the rest of them right now. This is a 2-point source, right here, these two. And you know if there's a if the path difference here, and they're going off to a field point here. I've drawn these as parallel because the field point is far away. That's our assumption, right? We're in the far field. If there's a half wavelength path difference here, the superposition of these two waves here is going to give you 0 because they're 180 degrees apart, right? And it also could be, you know, it could be 3 halves of a wavelength. If it's just one wavelength, it's going to correspond to a maximum, approximately. So when I have this situation here, these two elemental sources here are going to give me 0 sound field. Well, now now let's look at the next two over. One right here and one right here. What field am I going to get for those two? 0. So I can go and I can sum over the whole rod here, and I conclude that when I have a half wavelength path difference here, or 3 halves or 5 halves, I'm going to have a pressure null out there. The total pressure will be 0 in the far field. And you can look at the geometry here. You can see that the sine of theta, you can see this is a right triangle. Here, there's a right angle. The sine of theta is lambda over L, right? That's precisely this condition here. If you set k equal 2 pi over the wavelengths, you precisely get this same condition. Okay, so I've already talked about this. So that's the way people usually tend to look at this, and that's the way we often do it experimentally. We often sweep frequency. And a lot of people do this in other fields, but it's especially true in acoustics. You saw this early on last quarter with just oscillators, right? Keeping the drive amplitude constant, slowly increasing the frequency, looking at resonance. So as we do this here, as we increase the frequency from a relatively low value where there are no nodes, we're going to get more and more as they will appear. They will appear out of the, theta is equal to plus or minus 90 here. They will appear and then grow as you decrease the wavelengths. So here's an example. Here's KL. The KL number is 24. And that lies in here. There's going to be 3 nodes. This is from the book. Okay, so here's our source right here. And remember, theta is measured from the perpendicular bisector here. So you can calculate, and we'll do an example of this, homework example, and probably a quiz. You can calculate the angles here just from setting, you know, this is the condition for a nodal cone. This is the nodal cone condition right here. And of course, by symmetry, they're on either side. They're going to be on either side. And we can exactly find the angles of the nodal surfaces in the far field. What about the lobes here? These are called lobes. And again, we have axial symmetry here. Here's somebody did this a long time ago. It's made out of wood. So this probably took a lot of effort, right? They didn't label it. That amazes me when somebody goes through all that trouble. They should have put a little plaque here. They did on one of, there's a number of these models. They did on one of them that we'll get into next week. So anyway, I think I'm going to add a label here. But it's pretty clear what this is. It's suspiciously very much like this, right? I'm pretty sure these are going to correspond. They're the same KL number. So this is a 3-dimensional version. The line source lies, you know, in here, and here like this, just like you see here. And you can see there's angles here where we get no pressure. Now, sometimes it would be of interest to find the maximums, right? And this is one of the reasons people like the pressure nulls. It's usually easier to solve for the maximums here. The maximums are hard to solve for here, the angles that the maximums occur. And we'll hit a problem like that in the homework, I'm recalling right now. But it can be done, of course. It just takes more effort. And when you listen to this, and when you're detecting it with a detector, or listening by ear, or with a microphone, it's usually the nulls that come out and hit you. That's what you, like in the anechoic chamber, you know, you're naturally drawn to those nulls. It's just it's something you can clearly hear, or not hear, I guess. That's one of the reasons people like nulls. These are analytically, you have to make approximations to solve for these here, these lobes. Now, you'll notice this looks kind of strange here. And they could have, I don't know if they're accurate here. Maybe they didn't, you know, this was probably done and they didn't have computers. You know, this book, the first edition of this book goes way back, right? Did we talk about this? I think it was 1960 or something like that. But anyway, but another reason it looks kind of strange is, this is not, this radiation pattern here, this is not the pressure amplitude that's being plotted along here. It's the logarithm. It's called the beam pattern. And the beam pattern is very simply defined to be this. It's a logarithmic measure. So you can, and basically people do it so that you can not lose the details of what happens when the amplitude goes down small. And you can see here they've written, it's got to be at theta is equal to 0. What's the beam pattern going to be? What's the directional factor at 0? It's 1. Log of 1 is 0. So everything's going to be negative dB, and then the maximum is going to be 0 dB. So everything's so many dB down. And that's what this is right here, 10 dB down. This is this arc, anything that's here. Like this point here is 10 dB down from the maximum. This is a useful way to do it. And one of the reasons, the main reason it's useful is, this is, you wouldn't see this structure that we're seeing here. If you did this on a linear scale, it would be all down here near 0. But because we're taking the logarithm, we're expanding those low values. Because the log of 0 is minus infinity. So that's the main reason for the logarithm here, for this logarithmic measure. So, and that's what this is. These curves here are supposed to represent the beam pattern. So what about the reference level? Well, this is a dimensionless number. And by convention, it's 1 at 0. So there's, you know, it's built in. Don't have to worry about it. Oh, why is it 20? Why is it not 10? Anybody? Where does the directional factor come from? Way back here. It's pressure, not intensity. Okay, that's why it's 20. It's an amplitude. It's telling you what the amplitude is, not the energy or the intensity. So that's why it's 20 dB, scaled by 20 dB. Okay, now, here's another model. Now, you know, I should have asked Professor Kopolka. This will come up in the underwater acoustics course, okay? But I just want to mention it here. There's another one of the other models that somebody made here. Is this? What do you think of this? What does this correspond to? Well, again, they didn't label it. Okay, went through all this trouble and didn't make a little plaque or something like that, which it just upsets me because I run the demo lab here, right? And we always try to label things if we can, so that people know what they are, at least have some idea of what they are. So can anybody have any? This is skewed, isn't it? This is symmetric about the perpendicular bisecting plane, but this is not symmetric. The major lobe, this thing right here, the major lobe is, instead of being like this, it's now lies along this cone in this direction. So how would you get that? And is it useful? No. Well, this is what you get from a so-called phased array. You've probably heard the expression before. So it's the easiest way to explain this, I think. Let's go back to our friend, the two-point source. Okay? Identical sources in phase. Here, we know we're going to get a maximum. right? There's no path difference. We're going to get a maximum. But suppose they're not exactly in phase. Suppose, let's say this one is ahead of that one. Where do I have to, what's going to happen to the maximum? If I'm here, the sound, a crest arriving from there, I'm going to get a crest a little time later from here. I want those crests for the maximum, I want them to be arriving at the same time. So what do I have to do? I got to go to a point over here. I got to increase this path difference has to be a little bit bigger to compensate for the fact that that's ahead in phase. Then they'll be in phase there. So my maximum, when they're in phase, it lies on this plane, right? When I put this one a little bit ahead of phase, what does that maximum do? It goes to, in the far field, it'll go to a cone, like that. It won't be flat now, it'll go like that. And I suspect that's just what this is. This is representative of a steer, it's called a steered array. Has anyone heard of that? Yeah. So a lot of times, for applications, you want a nice beam of sound. You want to be able to direct it, to detect things and bounce it off, okay? So one way that you can do this to control the beam pattern is to put a phasing in there, to steer it. You can always, mechanically steer this, but usually it's much easier to electronically steer it. So you don't have to actually mechanically rotate it. So we can't quite get to that in this course. It's going to be in the 3452. Okay, now finally here, this might seem out of place, but I want to drive home this fact that as you go to higher frequency, which means smaller wavelengths, you get a lot more nulls there, okay? We did something similar in the anechoic chamber, but we can do it right here. I'm going to turn on this amplifier and function generator. I've got just a single loudspeaker here, okay, and it's 100 hertz. So that's 100 hertz, right? The wavelength is roughly 3.5 meters. It's a huge wavelength. And we only have a single source, but we can get interference because there's the walls here. In fact, you can get a very complicated interference pattern due to the sound bouncing off walls. However, at this large wavelength, you can move your head around, or you can even walk around. You'll hardly hear the sound doesn't really change much, okay? It's bouncing off the walls, and we don't, the wavelength's so large we can't have any destructive interference. There is one exception. There's right around, I heard it, oh, maybe it's because the door was open this morning. The door's closed now, yeah. So this is an example. When you have a very large wavelength, you're not going to get any destructive interference. It's very hard to get. However, now we're at 5 kilohertz. If that's painful, let me know. You guys okay? Now, 5 kilohertz is a wavelength like this. All right? You may wonder, well, this is an extended source, so it's like a rod. It's similar to that. It's spatially extended. Can we get interference? Yes, and we're going to solve for that. That's a famous problem. Radiation from a piston. Famous problem. We're going to solve for that next week. But we don't have to worry about that. Even this is a point source. Even if it's a point source, we're still going to get an interference pattern because it's reflecting off the walls. So you can imagine all these image sources out there. You know you're going to get an interference pattern. You're going to get pressure minima, okay? Because the wavelength is so small here, now all you have to do is actually move your head a little bit. Rotate or move your head a little bit. Yeah, I'm going through nulls, minimums. They're not zero. It's too complicated to be exactly zero. But you can clearly hear going through maxes and mins. And you just have to move your head a little bit because the wavelength is so small here. Yep, there it is. famous problem, difficult problem. But going through it builds character. That's what I always say. And we'll do that. We have a problem session tomorrow and then the Helmholtz lecture on Thursday. So we'll do the baffled piston next week.